Okay, so hello again, guys. So this time we have 5.2 Planck's quantum theory. Okay, so Max Planck has this theory which is widely acceptable. So he tried to discover that when solids are heated, they emit electromagnetic radiation over a wide range of wavelengths. Okay, so for example, we have an electric heater. So if you tried to uh, make electric stove work, so sometimes there is a red glow in the electric pan, and also on the light bulb we have a bright white light. Okay, so if we have those colors in the visible region, so this means that there is a radiation which contains energy that are emitted. Okay, so emitted, so for example the electric heater, so if we try to put our hands on the electric heater, so it is very hot, so this means there is a transfer of energy. Or for example the light bulb, so after the switch is opened for example for a few minutes, the light bulb become hot because there is a transfer of energy from the tungsten uh, wire inside the light bulb to the surroundings. So this is the theory by Planck. And according to him, so atoms and molecules could emit or absorb this energy, but only in discrete quantities. So we have these tiny little amounts of energies that are being absorbed or being emitted by atoms and molecules. And these are discrete quantities. So we cannot have, uh, for example, zero point 0.1 scale or 0.001 scale. So it's just like a whole number for the atoms and molecules. And this quantitation of energy, according to Planck, so he made this as quanta or quantum. So quantum is the smallest quantity of energy that can be emitted or absorbed in the form of electromagnetic radiation. So how do we calculate this energy? So we have this formula is equal to h nu. So h is the Planck's constant. So this is the second constant that you must remember in this chapter. So nu here is still the frequency. So nu, we all know from the previous topic, is or can be also converted into c over lambda. So if any problem is given in wavelength and you need to find the energy, so this is just E is equal to h c over lambda. Okay, so this was the theory of Planck, wherein we have, or the uh, atoms or molecules could emit or absorb discrete quantity of energy such as quantum amount of energy. And Einstein discovered a phenomenon which is the photoelectric effect. So in this phenomenon, so electrons are ejected from a surface of certain metals exposed to light with a minimum frequency called the threshold frequency. So this is his formula in finding that minimum energy from the minimum frequency. So this is the minimum frequency nu naught. So this is a sub, the zero is a subscript. Okay. So for example, we have the automatic doors in the mall or in establishment or in hotels. So there is a small uh, beam of electrons coming from the topmost of the sensor in the automatic doors, so that will emit the radiation, And if we have, for example, we have metals inside our body, for example, we have iron or we have jewelries, so that radiation from the sensor would come to the metal, and then electrons are ejected, and these electrons are detected by sensors so that the doors would automatically open. So that is the most uh, or that is one of the contributions of the photoelectric effect by Einstein, the automatic doors in the malls. Okay, so let's have some problems from Planck's quantum theory. So calculate the energy. So take note that energy is in joules of a photon from the IR region and a photon from the X-ray region. So what we know of for now in this topic is we have E, or the energy, is equal to h nu. Okay, or E is equal to hc over lambda. Okay, so again, please pause this video and then try to solve this first in your own, and then we'll try to discover the answer after you play this again. Okay, so this is the solution. Okay, so the top part first. Okay, so E is equal to h nu, and we all know that nu is c over lambda. Okay, so we have E is equal to hc over lambda, so we just combine these two equations. Okay, so okay, so that is the Planck's constant. C is this speed of light, and then the nu, or the lambda, is given the wavelength. So for letter A, that is 5 times 10 to the 4 nanometers. So we can cancel the second in the per second, the meter into the nanometer, by first converting nanometers into meters. So again, plugging in those values in the calculator would give us 3.98 times 10 to the negative 21 joules. And then for B, we also have the same formula. So this time we just make the wavelength different. That is 5 times 10 to the negative 1 nanometers. Okay, so again, plugging in those values, converting nanometers into meters, okay, and then solving it using calculator, we'll get 3.98 times 10 to the negative 16 joules. So if we compare these two energies, so the X-ray, or the energy, is larger in the X-ray than in the infrared. Okay, so this means that X-rays are highly energetic radiation than infrared radiation. So this is why X-rays, or we are given 6 months as a maximum limit for just one X-ray session. But for infrared, so infrared are sometimes used in phones as well as in different communications. Okay, and in the 2000s, so if before, we do not have Bluetooth, but we have infrared as a source for transmitting videos or photos or music. Yeah. Okay, so much for the history. So we try to move on. Okay, so this is still part of the photoelectric effect. So electrons are held in a metal by attractive forces, and so removing them from the metal requires light of sufficiently high frequency. So that means that there must be higher energy that strikes the surface of the metal so that electrons are ejected. Okay, so this h nu here is the energy of the incoming radiation. So this must be equal to the sum of the work function, which is the energy for removal of electrons, plus the kinetic energy of the electrons. Okay, so if we try to find how fast the electron ejected is, so we try to find first the kinetic energy. So kinetic energy is solved by subtracting this work potential from the energy of the incoming radiation. So we'll try to have some problems also with this. So the work function of tissue metal is 3.42 times 10 to the negative 19 joules. So try to calculate this minimum frequency or the threshold frequency required to release electrons from the metal, as well as calculate the kinetic energy of the ejected electron if light with frequency 1 times 10 to the 15 hertz is used for irradiating the metal. So again, pause this video and try to solve this first on your own. Okay, so I hope this time you paused also the video and try to solve this. So this is the solution. Okay, so for the first part, you're asked to find the threshold frequency. Okay, so remember this. So E naught or the work function. So take note that E naught is also W or the work function is equal to H nu naught. So this threshold frequency, the nu naught, is equal to the work function divided by the Planck's constant. So just plug in the values and then we'll get 5.16 times 10 to the 14 hertz. For letter B, we're asked to find the kinetic energy of the ejected electron. So from the formula, h nu minus work function, so we just plug in the values of the Planck's constant, this frequency given on the problem, and the work function of tissue metal. So we'll get 3.21 times 10 to the negative 19 joules. So that's it for 5.2.